Just a quick video I hope we'll see. Requested video. Good question to ask. Again, my opinion, I think that this question is fair game for an exam. Don't think it's too hard, don't think it's too easy. I think it's just about right. Just my opinion. Not that my opinion matters whatsoever, but those are my 2 cents. I want to cover this example. I don't have much preliminary notes about it, just this. I've constructed, labeled 2 random variables. I have the lifetime of battery A and the lifetime of battery B, denoted by X and Y respectively. I have a picture. I have no picture, but I will have a picture. First thing is, let's just write down what it is we're after, actually. I believe the question says, let me just read it one more time. I think it says we want the probability that battery lasts more than 1 hour greater than A, right? Oh man, what does it say? We want the probability that Y, the lifetime of battery B, is greater than the lifetime of battery A by at least 1 hour, I believe. Always, as usual, read the question 5 to 100 times. This is what we want. Probability that Y is strictly greater than X plus 1. So we want the lifetime of our battery B to last basically at least an hour more than battery A. We are given that these lifetimes are independent. We definitely need that. And you should be thinking, when you have this kind of situation where you have 2 random variables that are basically laid out for you, you're going to want a picture, in my opinion. Just my opinion. Pictures help. Here's the picture I have. I mean, I hope you're not too confused by this sort of thing. This is just saying Y is strictly greater than X plus 1. So these denote my random variables. However, you can essentially translate this directly to the picture, just how you would graph a linear equation in 2 dimensions. Okay, of course everything's taking place in 3 dimensions, but we're just looking at this particular plane, the xy plane, and we want, we're interested in the equation of the line y equals x plus 1. Y equals x plus 1, no big deal. If I look in quadrant 1, it has this particular, shape, I guess you could say. It's a line, and we want y to be strictly greater than x plus 1. So you'd be thinking, okay, I'm a math expert, so I know this line has to be dashed. There, it's dashed. But you should also say, with regards to continuous random variables, it plays no role whatsoever. Regardless, we do want the probability that essentially we land in this region. We land in this region. And actually, come to think of it, they tell me what this is actually, right? They tell me what this probability equals. This is not actually what we're after. This is equal to 0.33. We want to calculate M. What is M? M is the mean, the expectation of X and Y. They're both exponential, and they both have the same mean. Y equals X plus 1. All right. So should I even write down the PDFs? Probably not. I mean, you know this like the back of your hand. I'm hoping that really that this question was asked because of, the setup. I don't know. I don't really know, but I'm going to go through it. Here's the situation. What is the probability that y is strictly greater than x plus 1? I can say this. Okay, we do have a double integral. I'll deal with the bounds in a moment. With regards to my integrand, this is where we use the aspect, the piece given that x and y, these corresponding lifetimes of these batteries, are independent. Okay, they both have exponential distribution, mean m. So what I'm going to do is this. This is equal to, the integrand is 1 over m e to the negative y over m times 1 over m e to the negative x over m dy dx. Hopefully you're quite familiar with the double integral game. Since I've written it this way, you know automatically I'm integrating with respect to y first. I've already made a decision by writing dy dx. Furthermore, this is the PDF of y, the PDF of x, my density functions, and I can multiply them. I can treat this actually as the joint PDF. Why is that? Well, because these are independent. X and y are independent, right? So this really is the joint PDF here. All right. Now, what are my bounds of integration? This is precisely why you have the picture. Okay, this is precisely why you have the picture. Now, the integration region is not a rectangle. So you should be thinking also, these are not constant bounds of integration. Therefore, the inner integral must have variable, at least one of its bounds must be variable bounds of integration. All right, the way that I imagine this is that y, since y comes first, y, the smallest y can be is down here, and I imagine an arrow shooting up, and it first hits the line, it first hits this line, and then it goes up this way. So it first hits the line x plus 1. As I mentioned, my first variable I'm going to respect to must have a non-constant bound of integration because my region is not rectangular. What is the largest y can be looking at my region? Well, it does go off to infinity, so that's what I have there. Now, for my outer integral, we will have constant bounds of integration. In fact, if you want this to be a number, it better be constant bounds of integration. So the smallest thing x can be, imagine coming horizontally, the smallest x can be is 0, and it goes off to infinity. Imagine, this line continues. X can be as large as possible, 0 to infinity. You may want to consider computing the complement of this or something, but I don't really see how it's any more efficient. Anyway, this is my probability, and we know this equals 0.33. So this is equal to essentially a third. All right, there. All right. We just need to compute this integral and we'll be done with it. When it comes to exponential random variables, particularly the exponential PDF, integration should be pretty straightforward for you. If it's not, you may have to do u substitution. If it is familiar, well, you just jump right to it, right? So this tells me now, the left-hand side, okay, this is one of the reasons why I did not multiply these together. Because look, with respect to y, honestly, you can almost treat this like two separate integrals. So this is equal to the following. Okay, so this is equal to 0 to infinity. Okay, and I'm just going to integrate this, of course, first with respect to y. So what is that going to be? Well, this is really the survival characterization of y. Okay, I want you to think about what I just said there. I'm not going to go through this. Just think about this is the probability. This is the probability, with respect to y, is the probability that y is greater than x plus 1. Again, do the integral if you need to, but you should be thinking this is a survival characterization of an exponential random variable y. So this is equal to the following, I claim. This is equal to e to the negative x plus 1 over m times e to the negative x over m. Let's put the 1 over m out here. So you may be thinking, what the hell just happened? If you're thinking that, go through the computation. Okay, I've done this. You need to have so much practice of this that you really just jump right to this step. Think about what I just said. This is the probability. With respect to y, it literally is the survival characterization. The probability of the random variable y is greater than x plus 1. It's this. Let's continue. Just do some algebra here to combine these two, right? If I have two exponential expressions with the same base, I just add the exponents. So this is now equal to the following. Well, this is equal to 0.33. Okay. I basically have, just need to combine these two. Why don't I just do that as a little side note here. So what is this integrand now equal to? Well, combine these. This is 1 over m e to the negative 2x plus 1 over m, right? I just wanted to combine the exponents. They both have the same denominator, so that's all good. That negative, by the way, is outside of the whole exponent. So in a way, there's parentheses around that exponent. And now I just integrate that. All right, not too bad. Not too bad at all. This tells me that I have the following. When I integrate that, it looks like I'm going to get this. Looks like I'm going to get negative a half e to the negative 2x plus 1 divided by m. And we know that this is equal to 0.33. Just a quick double check when you're doing this sort of thing. Differentiate this, make sure you get the integrand back. So with respect to x, I take the derivative, it's e to that power, times the derivative of that power. The derivative of the power is negative 2 over m. The 2's will cancel, and I get 1 over m, which is right here. So this looks good. This looks good. This is not x, though, is it? I'm going to infinity here, okay? Why don't I put this? Why don't I do this? 0 to infinity. All right. When I plug in infinity, we really need an improper integral. We're not doing that, right? We just want to get straight to the answer. When I plug in infinity, I get 0. When I plug in 0, I get 1 over m. So this is the situation I'm getting here. This is now equal to 1/2. The left side is a half e to the negative 1 over m. E to the negative 1 over m is equal to 0.33. This is looking good. This is looking good. Maybe just one more step. Let's get m by itself. If I want to get m by itself, I multiply by 2, then take the natural log. This looks like I have, well, let me write it this way. This is negative 1 over m is equal to ln of 0.66. So I multiplied by 2, gives you 0.66, and then take natural log of both sides. Let's isolate m. This tells me that m, just do some, however you want to do it, just algebra, reciprocal both sides, multiply both sides by negative 1, and we get m is equal to negative 1 over ln 0.66. Don't freak out because ln of a fraction is negative, which means m is positive, and when you input this into your handy dandy calculator here, you get the TI-30XS, right? You get a 2.41. So this is 2.41, and that takes care of it. Again, I recommend, just a brief thing to say here, go through this computation and get to the point. I'm recommending this to all you exam peers. Get to the point where you've done this kind of thing so many times, you don't need to do substitution, no nonsense, you literally just jump right to it. I mean, how much more efficient can you be with a double integral like this? It needs to be automatic. Alright, I hope this was helpful. Thank you for requesting the video, and tell me what you think.